Hello. Am I audible?
Yes, Dada.
Okay. You can see my screen, right?
Yep.
Okay. Good. So what were we doing in the last class? I mean, till what was the exact point where I had left off? Possibly I promised you that I would prove parents' criterion, right? Anything beyond that? I don't recall.
No, the last thing that was done was parents' criterion.
Okay. Okay. So let me restate the criterion for you. So we have B harmonic irreducible, harmonic polynomial with the constant term not equal to 0. And the polynomial looks like this. And we are given a very strange inequality that says that, sorry, this is monic, so I should omit this. Then I need to show that Px is irreducible. This was the criterion, right? Okay.
The right hand side of the inequality should start from a n minus 2, right?
Sorry, yeah, definitely. Yes. N minus 2. Okay. So before looking into a proof of this, let's try to do something easier. All right. So let me present it as a problem for you. So I have px in zx, a polynomial with integer coefficients. Okay. So px is, let's say it's not monic. It's a1x plus a0, right? Now we have a criteria that a0, that is the constant, the modulus of the constant term, mod of a0 is prime. And additionally, this is greater than the sum of all the other coefficients, the modulus of the sum of all the other coefficients. All right. Then show that px is irreducible in Zx. Is the problem clear to everyone? I mean, I'll show you the statement once again. So px is essentially a polynomial with integer coefficients, and px can be, so px is a(x power n plus dot 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 all the way up to a1x plus a0. You have the criteria that modulus of the constant term is a prime number, and this modulus is greater than the sum of moduli of all the other terms, of all the other coefficients. Then can you show that this polynomial is irreducible?
Yeah.
How do you show?
If this polynomial has any complex root, then its modulus should be less than 1. If it is greater than 1, we can show contradiction by triangle inequality.
Right. So how do you show that modulus of any root, say the root is theta? So how do you show that the
summation ai theta to the power I equal to 0, and mod of a naught equal to mod of a1 theta plus up to mod of n theta to the power n.
right?
And if it is greater than equal to 1, that should be less than summation mod of ai.
a1 theta is equal to theta square all the way up to an theta to the power. Can I have your name, please? What is your name?
Ritabrata.
Okay. So I this is my assumption that suppose mod of theta is less than equal to 1. Okay. Now
Should be greater than equal to 1, because
I mean I'm working under the okay,
we
sorry.
have to
Right,
show that it should
right.
be less than 1.
Right. So what I want to show is that, so what do I have? No, I see what I want to essentially do is that I want to show that mod of theta is less than equal to 1. So let me assume that mod of theta is greater than 1. So this holds, right? Which is a contradiction.
Yeah.
So now I should have mod of theta less than equal to 1 for all roots theta of px, right? This is by triangle inequality. By triangle inequality. All right. Okay. Now, suppose Px is reducible. All right. Okay. Then can someone tell me what A0 is in terms of Qx and Rx?
Q0 R0.
0. Now you know that. Take modulus on both sides. What do we have? Now what we know that this is prime, right? So what can you say about
One of
Q0
them
and
should be
R0?
one.
One of them should be 1. So without loss of generality, let us assume that mod of Q0 is 1. Okay. And all right. So suppose the degree of Qx, take it to be something, maybe, I don't know, K. All right. So now this has K roots, K many roots, complex roots, right? So what can you say about the suppose are the roots of Qx? What can you say about yes? This will be essentially the reciprocal of the leading term coefficient of the polynomial Qx, isn't it?
Yeah.
Okay. Is this clear to everyone? I mean, that suppose Qx is equal to something like say, I don't need anything. I mean, I just need the coefficient of the leading term of Qx, isn't it? So let the leading term coefficient of Qx be alpha. All right. So can we say that this is by Vieta formula, isn't it?
That should be less than 1.
And that should be less than equal to 1. Is this clear to everyone? I mean, just Ritobruta is talking, so no one else is responding.
Yes,
Yes?
it's clear.
Okay, it's clear. Cool. So now can we have a contradiction from here?
Yeah.
Yes. What will be the contradiction?
These phi's are also root of the original polynomial.
Right,
Their
exactly.
modulus should be greater than 1. So this product should be greater than 1. Because each of them has modulus greater than 1.
Right, right. Okay. So we observe trivial observation that are the roots of Px as well. right? So mod of phi I is greater than 1 for all I. Which implies phi 1 to phi k should be greater than 1. Contradiction. Okay. This is fine, right? So why did I suddenly introduce this problem? This is a good problem. It's another way of looking at solving irreducibility of, testing for irreducibility of polynomials, looking at the complex roots, right? And providing some bounds on the coefficients and such things. Okay. But this I did to familiarize you with such arguments that we might need while proving parents criterion. Okay. So now we will take up the job that is left from the previous class and prove this. Okay. All right. So we have a monic polynomial. And we have this constraint. Okay. In order to prove parents criterion, we need a small lemma. I wouldn't say a small lemma, but all right. So if a polynomial Px satisfies the above inequality, monic polynomial, okay, then the roots, I should say that then only one root of Px lies outside the unit circle and all the other roots lie inside it. Note that none of the roots lie on the unit circle. Is this statement clear to everyone?
Yeah.
Okay, so just one root of Px satisfies the equation mod z greater than 1. So this is essentially in our Cartesian coordinates x squared plus y squared greater than 1, right? So if the root is x naught plus I naught, there is only one root x naught plus I naught such that x naught squared plus y naught squared is greater than 1. Remaining all the roots, so let me denote them by xi plus yi, where I ranges from 1 to n minus 1. Okay, the remaining roots, they all will lie inside the unit circle. That means xi square plus yi square will be less than, strictly less than. And there is no xi yi such that xi square plus yi square is exactly equal to 1. Okay. Now, let's see that. So, Ritabhuto, can you tell me that how this lemma can be used to prove parents' criterion?
I'm thinking.
All right. Take 1 or 2 minutes, I guess. So use contradiction, maybe. So the hint is use contradiction.
Sir,
Yeah.
sir,
Go ahead.
I just joined. So can you give me a quick recap?
Oh, quick recap. So whatever I have been doing is essentially on this board. So I started with the statement that I left unproved in the last class, which was parents' criterion. I stated that once again. And in order to motivate such, I had previously mentioned in the last class that this proof will require complex numbers. So in order to motivate such proofs, I gave a rather well-known problem, which is written on the board again. I need to show that this polynomial px, which satisfies this given inequality, is irreducible. And then I use complex numbers and contradiction to prove that. That's all we have done so far. And now we are looking at the proof of parents criteria. And while doing so, I stated a lemma which says that if a monic polynomial px satisfies the inequality that is stated in parents criterion, then only one root of that polynomial will lie outside the unit circle, and remaining all the other roots will lie inside the unit circle. And there will be no root that will be precisely on the unit circle. Okay. So now we will be using this lemma to prove parents criteria, and then we will possibly look at a proof of this lemma.
Sir, one thing.
Yeah.
I may be wrong, but as far as I remember, that what was it called? Conjugate of the root, conjugate of one complex root will also be conjugate will also be a root.
Yeah, that's perfectly true. Okay.
Yes. So therefore, does it not mean that the root that lies outside the circle is a real number?
I'm sorry. I mean, conjugate and the original complex number have the same modulus, right? So yeah, I mean,
Yes. If only one root
yeah,
is outside,
right.
that
You're
means
right.
that
Okay,
means
so
that,
how do you use this fact?
like I am just mentioning it. I
Your
don't know.
observation is right. Yeah.
Okay, modulus equal to. I can prove that no root can lie on the unit circle.
But that is not related to parents criterion, is it? I mean, that is not essential for the proof. Okay, we will get into that. I'll ask you that when we start proving the lemma. But now, as of now, I'm telling you to use this lemma and prove what we want to prove actually. Maybe I'll give you leads here. So suppose px is reducible. Suppose All right. See, now I know that exactly by the lemma exactly one root of px lies outside the unit circle. So assume that lone root is the root of Rx. That particular root
Oh, in that case, we get mod of Q0 less than 1.
right. That's what I was trying to arrive at. So if that is the root of Rx, then all the roots of Px Qx lie inside the unit circle. Right? So what do you get? Mod of Q0 is less than 1. But can it be? Why is it so? Because mod of Q0 is nothing but let's say the
product of
root
roots of
the
Qx.
product of roots.
The modulus of the product of roots.
Product of roots. This is a product sign, not pi. Product of roots. So if that is less than 1, it cannot be less than 1, right? Because these are integer valued polynomials. Isn't it? So the constant term of Qx cannot be less than 1. This is a contradiction. So essentially, the lemma reduces the proof of parents criterion to a one-liner. Okay. Now the difficult part is to try and prove the lemma. So yeah, now I will ask Kritobrata to go ahead and tell me that why none of the roots lie on the unit circle.
If one root lies in the unit circle, so we take again we do again the same thing. That
Yeah, suppose the root is alpha.
inequality.
Right, triangle inequality.
So we have
That's
mod
why
of
I gave you the previous
alpha
one.
to the power n equal to 1, and we can show contradict
Yeah.
the given conditions.
Exactly. So what do? So we just plug this root alpha into that polynomial. So we look at T alpha. So that will be alpha power n plus alpha n minus 1. Sorry, I'm sorry. N minus 1, alpha n minus 1, all the way up to a1 alpha plus a0. Right? So now you can take this thing on the other side. Why am I taking this particular thing on the other side? Because I have such a criterion, right? I have this criterion. So I will possibly have to, if I want to prove or disprove such a thing, this note, if I want to prove or disprove this note, then I definitely have to look at whether this statement holds or not, this inequality holds or not. So that's why I am taking this term on the other side. All right. So if I take this term on the other side and take modulus, what happens is I get mod of n minus 1 is equal to mod of the entire quantity on the other side. Okay. Now it's just again an application of triangle inequality. That will give us
We
1
get the
plus.
opposite of the inequality in the criterion.
Right. Exactly. So I should do it. A0 plus A1. Contradiction. So the alpha equal to 1 case is ruled out quite trivially. Now, okay. let us look at the other cases. I mean, we have to show that one root lies within the unit circle and the other root lies outside the unit circle. So first, what I'll ask you to show, which is very trivial, easy to show, that all roots cannot lie inside the unit circle. True?
I have showed
Do you
this.
agree? Yeah? Yeah, go ahead. So it will just be, I'll look at the product of roots, right?
Yeah.
We can look at the product of roots,
Yeah.
we'll get the inequality.
So this is easy to show. So there is at least, this implies at least one root lies outside the unit circle. Okay. Now let me denote the roots by alpha 1 dot 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 alpha n. Without loss of generality, I can assume that alpha 1 is greater than 1. Fine. Okay. So now remove x minus alpha 1. I mean, divide the polynomial px by x minus alpha 1. Okay. So now I get a polynomial qx of degree n minus 1 with roots alpha 2 dot 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 alpha n. Note that these might not be distinct roots, all right? I mean, repeated roots is definitely a possibility. Okay, but I will show that actually, I mean, alpha 1 cannot be repeated. So what is my agenda here? I have, what I need to prove is that this at least is not at least. This is exactly. That's what I have to show.
Sir?
Right? Yeah.
So then Q of x must have product of root less than 1.
Right, lovely. So all the roots of qx must have, this is what we have to show actually, that all the roots of qx must have modulus less than 1. Right, so we are getting close to the point. So let qx, so if px is monic, qx is also monic, and it's of degree n minus 1, n minus 2, x power n minus 2, dot 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 b1x plus b0. Okay, and we know its roots are this. Okay, and we also know that px is nothing but x minus alpha 1 into qx. Let us quickly try to compute this product. I'm not asking you to compute the whole products, maybe at least the first one or two terms. That will be necessary, I guess. So this will have, the first term is definitely x power n. And the next term is b n minus 2 minus alpha 1 x power n minus, okay, just a second. So I missed a term. We should have minus alpha 1 x power n minus 1 plus bn minus 2 minus alpha 1 x power n minus 2 plus dot dot. Okay, right? I can even have something like a recursive formula for the remaining terms, can't I?
Sir, bn minus r minus bn minus r minus 1 minus alpha r.
Right.
That will
So
be
AR is B R minus 1 minus alpha R, right? So, sorry, I mean BR into alpha 1, isn't it? Okay. So, but I possibly won't need those. So let's look at something. I mean, have I calculated the coefficients correctly? I'm suspecting my calculation. Okay, no.
So,
See, right. This should be the power n minus 1. Yeah.
Yes.
Right.
Bn minus 2 is the coefficient of x to the power n minus 1 if we multiply.
Right. So let me rewrite this. So please correct me when I'm making computational mistakes. I'm prone to making such mistakes. Okay. So now I know that this is nothing but n minus 1.
So now we will compare the coefficient and then use that inequality.
Yes. Now we'll compare the coefficient and use the inequality.
To get a
Yeah. So essentially whatever we are doing is trying to arrive at contradictions for so long. Okay. And so tell me, how do I proceed? So I know that this is essentially n minus 1. Now what do I do? I can use the criteria that I'm given. All right. Now I can use the recursive formula.
Yeah.
Okay. So this will be b n minus 3, right? Minus b n minus 2 into alpha 1. Next term will be b n minus 4 minus b n minus 3 into alpha 1, and so forth up to the last term. What is the last term? Okay, I should have mentioned
B not alpha 1.
B not alpha 1. Okay. Now
we know that mod of alpha 1 is greater than 0. So we take mod alpha 1 out.
we will take mod alpha 1 out. I mean, can you tell me the entire thing then?
I'm thinking.
This is, oh, sorry. I put an inequality sign here, right? This should be an equality sign. This is exactly equal. We can use triangle inequality, the other side of triangle inequality, right? That mod of x plus y is greater than equal to mod of x minus mod of y. Rather, I should write this. Everyone is comfortable with this version? Do you know how to prove this? This is very silly, but okay. Is everyone sure that this holds? This is true?
Yes, sir.
Okay, cool. Still, I'll mention maybe trivially by triangle inequality. This is greater than x minus y plus b. So mod x. Take this on the other side. Okay. All right. Now, okay. Now gather all the terms having alpha 1, mod alpha 1, and then I can write this is
1 plus
mod of bn minus 3
and dot of 2.
I have no. I will. What I will essentially do.
Yes, then we'll take alpha 1.
Alpha 1 minus. I can take alpha 1 minus 1 common actually, right? Isn't it? Can I do that? Because
Yes,
see,
yes, yes, yes. Then we'll get the
Yeah.
terms will,
from here
quotients will cancel
and
out.
here, sorry, use the eraser by mistake. Bn minus 3. From here and here, I can take alpha 1 minus 1 common, bn minus 3 common, mod of bn minus 3 common. So the only term that I'll be left with is essentially what I'll get is this is equal to 1 plus bn minus 2 plus mod of alpha 1 minus 1. I've taken it common. What will be all the terms?
Bn minus 3 plus bn minus 4, like that, plus b
bn
naught.
plus dot 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 mod of b1 plus b naught. Right.
Isn't it
And-
1 minus mod alpha 1? Opposite sign.
It should be opposite sign. Why should it be so?
Because
Yeah. Right. You're right. It should be 1 minus mod alpha. Okay. Rather, I can do another thing. Maybe I need this to be greater than 1. See, because I'm going in that direction of a contradiction. So I have to bring something like that. So maybe I will apply the inequality, this inequality, in another way. Like I will take this minus and this to be plus. Can I do that? It's perfectly all right to do that, isn't it? I can take this to be plus and so forth. Okay. Instead of, I mean, this is greater than mod x minus mod y. It is also greater than mod y minus mod x. True? That's what I am doing. Okay. Now I can have this alpha 1 minus 1 common.
But about that term where it is mod bn minus 2 into alpha 1, where will that term go?
There is a mod bn minus 2 into alpha 1 term here, right? There is only one term. So by my assumption, alpha 1 is greater than 1, right? So this will be mod bn minus 2 into alpha 1 will be definitely greater than bn minus mod of bn minus 2. So that's what is appearing here. And from all the other terms, I've taken alpha 1 minus 1 common.
Then that will be a inequality, right? Instead of
Right. This will be an inequality. True. Okay. So if I have this inequality, then what do I do? See, I mean, this
So do we
by triangle
do
inequality
something with that?
Yeah. So I can show use triangle inequality on this. I mean, this is greater than this, right? Now my bn minus 2 gets cancelled from both sides, is it?
Yes.
But I'm still facing a problem somewhere. Just a second. Let me look at the proof. This is not falling into place. I need something else. Will this okay. No. I can do something. I can keep the inequality as it is. And I can keep the equality as it is, that is. Okay. And I can perhaps add a mod of bn minus 2 term here. Can I do that?
yes.
I can do that. Right. Lovely. Now I will have what I want. Okay. Because I need all the coefficients, sum of all the coefficients of the polynomial qx here inside this. Right. So now I know that this is greater than that. So finally, I will conclude that mod of alpha 1 is greater than 1 plus mod of alpha 1 minus 1 into mod of bn minus 2 all the way up to mod of B1 plus mod of B1. This is fine, right? Okay. So what do we have from here? That mod of Bn minus 2 plus mod of Bn minus 3 all the way up to B0 is less than 1. Now we are almost done.
Can you go back to the previous page?
Yeah.
Is it less than alpha 1 greater? Okay, got it.
Got it? Okay. So this is less than 1, right? Now we are almost done, since suppose now, for the sake of contradiction, what I want to show alpha 2 all the way up to alpha n, that is roots of qx.
So since all the bn minus 2, bn minus 3 all are positive, so mod of b0 must be less than 1.
Mod of b0, yeah,
Must be
mod
less
of
than
b0
1.
must be less than 1.
So then we can then use product of roots
No, we cannot.
for q of x.
What I want to show that all roots have modulus less than 1, right?
Yes,
So what
for q of x, the constant term is b0,
I mean, if there are some roots which are greater than 1 in modulus and some roots which are less than 1 in modulus, then also the product of the roots can be less than 1, right?
Oh, yes, yes.
Yeah. So suppose that root is alpha. Okay. So what do we have? Q alpha should be 0. This is equal to 0. And this is equal to something like alpha power n minus 1 plus beta n minus 2, alpha power n minus 2 plus beta 1 alpha plus beta 0. Okay. So I mean, this is turning out to be a somewhat long proof, but the methods involved, please carefully note down the methods that are being used. Triangle inequality at every stage, modulus of complex numbers, and such things. They are very crucial in difficult problems involving polynomials, not just irreducibility, but various problems. We'll see. Okay. So this will be greater than, does anyone object to this?
Sir, alpha must be less than 1. Otherwise, if alpha
is less than 1, then
upper part. If alpha is equal to 1 or greater than 1, then this will be obviously
this will
greater
be greater than 0. Yeah, that is what I was trying to show. But okay, so how do you prove it formally?
First, we know that we break this down into using triangle into each modulus, like mod of alpha n minus 1.
Yeah.
Yeah, so this is less than equals to.
But that
mod.
won't lead me anywhere. You definitely have to use triangle inequality, but you have to use the other side of triangle inequality in some sense. What do you have? Keep this in mind. You have this, right? Sorry.
Yes.
This is what you have. So that
So
means
you have to break down into those modulus.
yeah. So what do you essentially have? You have this is greater than 0, right?
Yes.
So you have to bring this factor somewhere in this from here, isn't it?
Oh yeah. So that will be greater than equals to mod of alpha to the power n minus 1 minus of
all the terms.
Yes, sir.
Okay. So if I take mod of alpha to the power n minus 1 common from here, I'll have this
minus of all that mod of b.
Fantastic. So this is greater than 0. Quantity. So X has all roots inside the unit cell. And we are done. Okay. Anyone has any trouble in understanding this proof? Then you can tell me. Everyone has understood, right? Okay. Have you seen this problem before? I'll give you a similar complex theoretic problem. I mean, this is a very popular problem. So just a little digression from what we are, our course of study. Let me have px a polynomial, which is maybe, how should I give you this problem? Okay, let me state it in this manner. Px is a polynomial which is 1 plus 2x plus 3x squared plus 4x cubed. No, I'll not make it an AGP series. So I'll probably break the norm. Maybe I'll allow it this to be terms of the Fibonacci series. Okay. 8x power 4 plus 13x power 5. Okay. Show that all roots have modulus less than equal to 1. I could have taken it to be honest, I could have taken the coefficients to be any, no, I'd probably try this out first, then I'll give you a broader version of this. Anyone has any idea how to go ahead with this problem?
Sir?
Yeah. Yes.
We noticed that 5 plus 8 equals to 13 and 1 plus 2 equals to 3 and 3x square is even. I mean, it will always be positive.
3x square is even.
Yeah, I mean, it will always be positive, right? Positive greater than equal to 0.
Yeah, positive, but not even, I guess.
I mean, 3x squared. that function. Okay, it will be greater than or equal to 0. So if we take
Yeah.
mod on both sides,
Let's go ahead with what you were saying. Okay.
mod of p of x equals to 1 plus.
You
is
want to
equal
use triangle inequality, right?
Yeah.
Is that okay? So 1 plus 2
Yeah.
mod x. This is what you want to do?
Actually, I did it differently.
Okay, go ahead. I want to listen to you.
So I did greater than, I did the other way around, greater than equals to 13 times mod z to the power 5 plus 3 times mod z square, because that term is positive. Then I took all the other terms negative. Z mod z square minus, and all the terms negative plus.
And then
Now we know
am I
that
missing out any term?
if if z is mod, then this cannot be 0.
This cannot be
0 if mod z greater than 1.
if
So we
mod
cannot
z
have.
is greater than 1, then this cannot be 0.
Yes, sir.
Okay.
So we won't have any roots in that case. Because if p of x 0, then mod
No,
p of x is also
I
0.
was talking about complex roots. Are you taking into consideration complex roots?
No, but we are taking mod, right? Mod of z.
Yeah.
So
Okay. So you are looking at the modulus. Okay. Fine.
So mod
So-
of z cannot be greater than 1 in this case here. Because if mod z greater than 1, then mod of p of x won't be 0.
Mod of p of x won't be 0.
Yes.
Right. Okay. So your argument crucially relies on the fact that this 13 plus 3 is greater than the sum of all the leading term coefficients, right?
Yes, sir.
This is 16 and this is
That and
something
also that z mod z square will be positive. So like mod z, that part will be, when z square is always positive, that is also that.
okay. So I just want a little clarification. Correct me if I'm not understanding this. I mean, you are first assuming that some root has modulus greater than 1.
Yes.
Okay. And then you are saying that if that some root has greater than modulus, I mean, this should be definitely greater than 16 then.
Yes, sir.
And what are you doing with this?
So that we are comparing and then finding. Like for example, 13 is the coefficient of the power z to the power 5.
I mean, so what you are essentially claiming is that if mod z is greater than 1,
Yes, sir.
then 3 mod z power, then 3 mod z power 5 plus 3 mod z square, 13, is always greater than
Yes, sir. That plus 1.
all right. Okay. But suppose I do a little mischief and I make this 11. Does your proof work?
Then this, it may be, then we have to do a little bit more algebra. I'm not sure.
I mean,
if this
you are
method
not
will
sure
work.
that this works, right?
Yeah,
You cannot
not
say
guaranteed.
it will work. Right. So you see, there's a problem here. I mean, now I will present you the problem in full generality. Let the coefficient sequence A0, A1, all the way up to An be a positive non-decreasing sequence. Okay.
Yes, sir.
Then Px is equal to n x power n plus n minus 1 x power n minus 1 all the way up to a1x plus a0 has all roots with modulus is n equal to 1. Much stronger statement, right? Much general, includes all the things that we know.
Okay, sir. If
Yeah.
we take x to the power n common,
Sorry, what is f?
x to the power n.
Oh, x to the power n you want to take common.
Yes, sir.
All right.
Whole into n plus n minus 1 by x, and like that will go.
I'm sorry, x power n minus 1. Fine.
And now can we take mod and use the triangle inequality and see something
Go
else?
ahead, go ahead, finish the argument. Take this, then
Then that is greater than equals to.
suppose this I mean there is a root of modulus greater than 1
Yes, sir.
such that this is 0 and mod x is greater than 1.
Yes, sir.
Now,
Sir, now this that right hand side is greater than equals to.
right hand side is greater than equals to.
Sorry, not greater than equals to. Wait, less than equals to.
How does that help me? I mean, okay, sure. Let's. I mean, yeah. All right. Okay. What do you want to do?
Then we can split that up into x to the mod of x to the power n whole into mod of n plus mod of n minus 1 by x, like that. And see if it
Minus, right?
Yeah.
Okay. Fine. Yeah. Then
I think it will be greater than equal to here. That inequality sign.
yes, this will be greater than equal to. Lovely.
Then I don't know. Like this seemed like something you can do with.
Okay. So perhaps this will be a little. I should probably give you a hint here. I mean, this triangle inequality and every such.
I'm just guessing because it seems like for a polynomial, if x is large enough, then it will be positive, and that's sort
For
of
large
idea
x,
using
right?
here.
So you're looking at for large enough x. What
Large
happens?
enough, then the polynomial works like the leading term.
Right.
Then
And then this, all these terms will be small essentially, right? These an minus 1. Okay, cool, fine. But I can't see at the moment that how do I get a direct. Ultimately, what I want to show is that this is greater than 0, right? So I don't see how we can get a concrete argument for that. Perhaps this will. Suppose I consider maybe a larger polynomial which has 1 as one of its roots. Okay. Say qx, I define it to be this colon equal to stands for defined in standard mathematics literature. And suppose I define a polynomial in this manner. All right.
Yes.
Then any z with mod z greater than 1, which is a
Will
root
give
of
us a
qx,
net.
is
It
also
will
a root of
give
this.
us a negative value.
Yeah.
Yes.
Okay. So any z with mod z greater than 1 is also a root of qx, right?
Yes, sir.
Now can you do something about this problem?
Also, since we are taking 1 minus n.
Yeah. Let me write down on a fresh page. Let's see
You
what you're
probably
saying.
have to arrive at a contradiction using that it gets.
So I do something that qz is equal to 0, and I put here. I'll look at the mod probably. So this is mod z. Sorry, this is z into pz. Now
Z is greater than. If mod z is greater than 1,
if mod z is greater than 1,
then 1 minus z mod will be.
this is greater than. I mean,
Can we use the triangle
we can
inequality?
use triangle inequality like this.
Yes.
Isn't it?
Yes, sir. And if mod z is greater than 1, we'll get a negative number.
No, again, see, you have a clash of inequalities here. So if mod z is greater than 1, then 1 minus mod z is less than 0.
It's
Fine.
negative.
But then I cannot write another this here. I have an opposite inequality arising here. Something does not seem to work here. But maybe we can just do some algebra on this qx, this newly defined and mysterious qx, and see why this was defined. You'll see in a short while why I am defining qx in this manner. Let's write down. Let's take some pens and write down what qx should be. What is qx? Qx is essentially, I don't know, minus n x per n. What should be the next term?
Sorry, n minus an x over n plus 1.
Dada, are we trying to do something like how we actually calculate AGP series, the sum? Like we multiply by the
Right.
by x
Essentially
and
by the
then
common
shift
difference.
one
This was
term
what
and subtract.
I was trying to arrive at. Right. Right. Essentially, that is what we do, isn't it? This is essentially
That is how
something
I
like,
was trying the one with the Fibonacci sequence, but ultimately could not succeed.
right. Okay. Well, so with the few, this should have a same approach because this falls under the same class of problems, right? So did you get what you are saying? I mean, whenever you sum things like 1 plus x squared all the way up to x power n or x power n minus 1, let me say, what do you get into the denominator? Something like this, right? So I am taking this over here and trying to look at the numerator quantity and then arrive at a contradiction. This is a very common and standard trick. Okay. Anyhow, so this will look like. Please help me with the calculation here. I'm just too dumb at calculations. I mean, this should be a1 minus a0 possibly, and with x, and what should be the last constant term? Constant term should be as it is, isn't it?
So there should be another extra power. Like another extra power to the x to the power, it will be x to the n plus 1.
N plus 1, isn't it? Okay. But okay, you see, yeah.
And
N x
similarly, x to the power.
Okay, now plug in the root that has modulus greater than 1. Be a root. Plug this in. What do you get? You get n x power n plus 1 is equal to, let me take modulus directly over here. So n minus 1 whole power x power n all the way up to a1 minus a0x plus a0. Now we will get something like a, can we get something like a, maybe a telescoping sort of thing and try to achieve what
So
possibly
like we proved that lemma.
Yeah.
We got some
Yes,
alpha, then we took alpha minus 1 plus alpha. We can do that with here x.
Right. So for I can take the first term out, and then you're saying the modified version of triangle inequality we applied, right?
Yes, sir. So it is very similar to like how we proved that lemma.
Right.
Sometime ago.
Essential. Okay. So I can write this is mod of a0 plus. Okay, so I need not write mod of a0 because a0 is positive, plus a1 plus a0. Let me put z here. It will ease up the pressure. So z everywhere. What should this be? Z power z and all the way up to n minus 1 mod of z. Okay.
Yes.
Now, since mod of z is greater than 1, mod of z power n is greater than mod of z power k for all k less than n. So in place of these, you can z, and the next term is a2 minus a1 z mod z square. So in place of all these, you can substitute mod of z power n.
Yes, sir.
That solves the problem. What do you get? So what you get is an mod of z power n plus 1, that is equal to a naught plus a1 minus a naught mod of z power n, and the next term should be, this is obviously
Strictly less than.
strictly less than, this is a2 minus a1 mod of z power n all the way up to n mod z. Alright, mod z power n for clarity. Okay, so what ultimately remains, all the terms, there is some cancellation, right?
Yes. So a naught
Okay,
plus
I can
n minus
introduce
n.
I can introduce z power n here, strictly less than. Okay, so I had is a naught here. So if I introduce a strictly less than inequality and mod z is greater than 1, then I can write a naught is less than a naught mod z power n, just to ease the calculation, so that one more calculation cancellation takes place. This and this will get cancelled in that case. Okay, so let me just see whether I am doing everything correctly or not. What will be the leading term of this? I mean, minus a n x power n minus 1, but
So since a
yeah, we
is
are done.
positive,
We are done. Essentially, we are
we
done.
get mod z less than 1.
This is right. We are done. So this is mod of n into mod of z power n, right? So you, what you get is mod
You
z.
get mod z less than 1.
Convection. Fine. Is this clear, or I will go over the proof again, all over again? If a single person has any doubt, don't hesitate to speak up. I have no trouble in going over the proof again. So this is fine, right? Okay, we'll come back to some irreducibility problem. I mean, this has been somewhat heavy, I believe. So let's for some time look at one or two easy problems from the remaining criteria. What were the remaining criteria? Remaining classification that I suggested. One was the roots of unity. Roots of unity. Okay. So here is a problem from roots of unity. Suppose I have polynomials ax, bx, cx, and dx. Okay. And I have something like x power 5 plus x dx power 5 plus cx power 5 equal to 1 plus x square. These are very suggestive, you know. I mean, whenever you see things like this, the first thing that pops into mind is omega power 4 plus omega cube plus omega square plus omega plus 1. So even in such geometric series, not just geometric type series, where I mean essentially all polynomials are geometric type series. So what I want to mention is that where you have a possibility of forming a system of equations that will get your job done, just plug in the roots of unity of the degree of the polynomial, which is equivalent to the degree of the polynomial, or which is at least relevant to the polynomial problem you're looking at. Let me be more precise about this. So into dx, okay? We'll see in the course of this problem. Okay. So now show that 1 is a root of x. So I'm assuming that everyone here is familiar with nth roots of unity. Is it? Or do you want a quick recap? If not, then it's very suggestive. This problem is very suggestive. Put down.
Sir, if we take the roots of fifth power,
Fifth root of unity, right? Okay.
then x to the power 5 will be 1, and x to the 5 will be 1 for a.
Right. So you
Five
just need to.
equations and we will sum them.
That will be enough. What are the equations you are getting?
A of 1 plus 1 times b of 1 plus c of 1 equals to 5 times.
So on the RHS, everything will be 0, right?
Yes, sir.
Always the RHS will always be 0. Anyone has any doubt regarding that?
Sir, but to cancel out the b part,
Yeah.
we have to also take 1. Then it will be 1 plus omega square.
Yeah.
Omega.
So 1 is definitely a root of. It's a part of the 5 roots of unity, right?
Yeah, and from there b and c will be cancelled, so a will be only left.
Okay. So let me just write down for ax plus 1 into 0. I'll write down all the equations. So you see, our polynomials class is mostly turned into a complex numbers class today. Complex numbers is very crucial. If we have time in the later part of this workshop, then we'll see more of geometry using complex numbers. It will be
Brother,
another.
can you shift to the previous slide for a second?
Yeah, sure.
The question was given that a of x to the power 5 plus x b of x to the power 5
Yeah,
plus
so
c of
if
x to
you
the power 5.
plug in any root of fifth root of unity, then that will always give a1, right?
Brother, I think there should be something before C.
X squared, it
Oh,
was
yes,
Yes,
already X
that's why
squared.
I was
Right,
asking.
right. I missed the part. There should be x squared there before C. Okay. This is also somewhat known problem from USMO. So let me write down the source. This is some USMO. I don't remember.
So the second equation should be a little bit different. I mean, we have x squared before c, right?
Absolutely. So this will be again just omega, right? This will be omega cube. And for the last part, I will have a1 plus b1 plus c1. These are my 5 equations. Now, go ahead. Let me number these equations for your sake. This is equation 1, 2, 3, 4, 5. Now what do I do?
Add
Add
all of them.
all of them. What does that give me? I mean, all
The B1, C1 coefficient is 0. It's 0.
We'll get A1 equals to 0.
So from there we get A1 equal to 0.
from there we
Is
get
equation number 5 correct? The right hand side.
Oh my word! Yeah, that is why the problem was getting so simplified.
5d of x.
Yes, now try it out. That's why I'm thinking that it's not a trivial J-immense problem. So what you essentially did was the special case that dx is equal to 0. Then I guess there was nothing to prove in the first place. Was there? Dx is the 0 polynomial, then your argument works. But here dx is any general polynomial. Yeah, any leads? Go ahead, at least add the first 4 equations. Leave out the last one. It has an extra variable. So maybe just deal with the first 4 equations at first. Is there any redundancy in this system? Do you know what redundancy means?
Yeah, when we have n equations, but n minus 1 equations are already enough.
Right. So is there any redundancy?
It seems like we can add the first 3 to arrive at A1 equals 0.
First 3. Why is that?
1 plus omega square lies as the coefficient for B1 and C1, so those two get cancelled out. Okay, no. Okay, no.
These are the fifth roots of unity, not your. Anyhow, go on. Add the first. Do what your intuition tells you to do at times. Add the first 4 equations, because that seems a way to get rid of these omegas.
Yeah, we are getting 2 equations. One is A1 equals D1 and then
A0
4
equals
A1
0.
equals D1 plus C1.
Sir,
A1 equals D1. How is that? I mean, B1 plus C1 equal to
You
0.
need to add all the 5 equations to get A1
We add all
equals
5
D1.
equations. We
Oh,
get 5A1 equals to 5D1.
Okay, A1 equal to D1. We are getting A1 equal to D1.
And
Okay.
adding the first 4, we'll get 4A1 equals B1 plus C1.
4A1 is equal to B1 plus C1. Anything else? I mean, you can still get more equations.
sir, A0 equals to D0. A0 equals to D0.
A0 equal to D0.
Yes, sir. Because of B and X are multiplied by X and X
But
square. So
yeah,
the
we
constant
are
term.
essentially complicating the problem by bringing it to 0, isn't it? We want to, our goal is straightforward. We want to check whether 1 is a root of A or not. So how does the evaluating the polynomial at a different point help me in that regard? What about let's see. I mean, I also need to think. I don't remember. Okay, look what we have here. See, I can get a very easy cancellation. Look at this. We have a omega here and we have omega here. Okay. We have omega power 4 here and we have omega power 4 here. Okay. We have omega 2 here, omega 3 here, and we have omega 2 here and omega 3 here. Now, does that give you any idea that if I...
Okay, instead of while adding the 4 equations, we are just grouping the terms of B of 1 and C of 1 together.
Right. So
Instead, we
do
will
do
just
that?
group in terms of omega, the powers of omega, and we can replace B1 plus C1 as 4A1.
Essentially. So if I do something like 1 plus 4 minus 2 minus 3, does that help me? The A1s get cancelled out. I get a relationship between B1 and C1, and that's what I need because of this. This is another one of those problems which is a bunch of system of equations and roots of unity. Maybe it should not take you that much of time from here. I mean, just write down the expressions. That will give you. Okay, I have to do the work then. So 1 plus 4. So omega plus omega power 4 b1 minus omega square, or maybe I should write it like minus omega square minus omega cube b1. And what I have is omega squared plus omega cube minus omega power 4 c1.
So taking common, we get b equals to c.
Right.
B of 1 equal to c of 1.
Is it done? I mean, b equal to c we get.
And b1 equals to
We get
b.
b1 equal to
C1.
Yeah, b1 equals to c1. That.
anything else. I need a little more. I mean, that's good, but that does not solve our problems. Still, we have some way to go. I mean, okay, this is a conclusion from this system of equations. b1 equal to c1.
But then we can
Now,
get
I need something.
coefficients in form of A1.
Then I can get the coefficients in form of A1, essentially. So
From there we can check.
but again, if you substitute, so what you're saying is 4a1 is equal to twice, I mean b1 is equal to c1 is equal to 2a1, right? So that solves our problem, because 1 plus 2 omega square is not equal to 0, right? Substitute in the first equation.
Yes, from there we'll get it.
Right. So A1 must be equal to 0. All right. Okay. So fine. Now what I want you to do is I want you to look at so this is how you use essentially roots of unity in polynomial problems. And I'll possibly provide you with other examples as well in a handout that we'll be providing tonight. But before that, we need to look into one more classification, that is divisibility by integers. I'll solve one problem in the class and I'll give one exercise for you to do. So let's look at a problem. So the result that we'll be using here is very, very simple. There's nothing, no much theory to cover. The only theory that we need to cover in the course of polynomials is mostly a little complex numbers, a bit of number theory. So those are all derived theory. The theory of polynomials, I mean, the thing that belongs to theory of polynomials and not complex numbers or number theory is irreducibility. So that's why I talked about that in much more detail than probably you would have known, but okay. So this is the result that we are going to be using here. So if a and b are two integers and px in zx perhaps be a polynomial, then a minus b divides b minus b. Do you want a proof of this or do you know how to do this?
We We can write the polynomial in its standard form.
We can write the polynomial in its standard. Everyone knows a proof of this fact, right? A minus b divides.
A to the power n minus b to the power.
Right. Okay. So proof, use this, and induction. I mean, this can be proven by induction, right? Yeah.
Sir, we can also simply use factor theorem.
Factor theorem, much more simple. Okay. So ak minus bk can be written as simply a minus b a power k minus 1 that solves it. Done. Okay. All right. So here is a problem. Another USMO. Suppose I have a polynomial px. Okay. In Zx. And I have the following constraint. PA. It's basically one liner. So all right. PA equal to B. PB equal to C. PC equal to A. Show that such Px cannot exist. Again, some USM.
We'll use the previous fact and then use modulus.
And use modulus. Can you?
Sir, there must be some relation between ABC, right?
There must be some.
Relation between A, B, and C, right?
Yeah, there is a relation which is as simple as ABC are distinct.
Yeah.
Integers, I should say for. Yeah, who was speaking?
Yeah, should I say the solution?
Yeah, any one of you can go ahead and tell me the solution.
Okay, px minus a equal to, we divide px minus a by x minus c and we get another quotient.
Sorry,
So
px minus pa
equal to x minus c into p suffix a x sub c. That is another polynomial.
p suffix ax. Okay.
Yeah.
Okay.
And we define px minus pb by at the
Similar.
same.
This should be x minus a, right? Right? P bx and define px minus pc. X minus b into pcx. Okay. All right. Then
Now we put x equal to a in those two equations, and b in those two equations, so that we put
which two equations? The first two or
we put x equal to in the second two equations. Sorry, I mean first and third.
so pa minus pb is 0. You have.
Yeah.
Sorry, no. I should write. I don't actually follow what you're saying. So you put x equal to a in. Let me now number this equation. Now
Wait. In second, put x equal to a.
into.
Wait. I have mixed up thing.
Perhaps something much more simpler.
We do it by using this. A minus c divides pa minus pc.
A minus c divides pa minus pc.
That will be b minus a essentially.
That will be B minus A essentially. Okay.
So
Next.
mod of A minus C will be less than equal to mod of B minus A.
Fine. Similar argument will give
Similarly,
you
we'll
that
get 3 more, and it will lead to a
it will
contradiction.
equal. This is again. Okay. So you have mod of B minus A is equal to mod of A minus C. Isn't it? Or perhaps I'll give you, so this is absolutely correct argument. So you will get 3 modular equations that are equal to one another. I mean, that's what you are suggesting. What is your name?
Shebanti.
Shevanti, right? So you are suggesting that this is one equation. I will have, and this is in turn, sorry, this will be in turn equal to C minus B, right?
Yes, and we'll get those numbers as equal, but they are distinct.
Yeah, but they are distinct. Okay. Another very simple second argument is A minus C divides B minus A. B minus A divides C minus B. C minus B divides A minus C. So from these two, I can get B minus A divides A minus C. So these two must be equal from here and here. B minus A is equal to A minus C. And by similar logic, equal to C minus B. Right? I mean, fine, all the arguments are just essentially equal. But, okay. All right. So now I'll leave you a problem for you to try. Have you all seen the question paper of ISI 2019? Yeah, has anyone seen? No one?
Yes, I've
Okay.
seen.
You have seen, right? So you must have seen this question as well. I mean, I will not solve it in the class because it's such a popular problem nowadays. But it will be very instructive of you to try it out if you have not seen it, or if you have seen the problem but you don't know its solution. And all it uses is this clever fact that okay, nothing else. With integer coefficients. Okay, so we define a sequence A0, A1 integers such that A0 is 0, n plus 1 is equal to f of n for all n greater than equal to 0. Prove that if there exists a polynomial, sorry, what am I writing? Positive integer m for which m is equal to 0, then either a1 is equal to 0 or a2 is equal to 0. Hint is very clear cut. Do you see what you have to what we have to do? I mean, you are given this relation, then how do you use this fact? This simple yet very astonishing fact. You will get something like n plus 1 minus n divides n plus 2 minus n plus 1 for all n, isn't it? Do you see that?
Yes, sir.
Yes, yes.
All right, so I want to end this class by a very, what I consider a very royal use of irreducibility, or royal theorem of, or problem of irreducibility. It has a name. It's called the Cohn's criterion. Okay. You can treat this as a problem. You don't need to remember all the names, but it has a very interesting observation. So what does Cohn's criterion say? It says that suppose you have a polynomial px equal to let's say n x bar n minus 1 x bar n minus 1 all the way up to n. Okay. And suppose, and one more thing, that coefficient of leading term is not 0. Okay. N is not equal to 0. Okay. Otherwise the degree gets reduced, so it has degree n. Now I tell you a very interesting thing, that n minus 1, n minus 2. So these are okay. So I have one more restrictions, that these n a0, a1, a2 all the way up to an, these are digits, single digits. Okay. And a0 is not equal to 0. Okay. And now I tell you that in n minus 1, n minus 2, n minus 3 all the way up to a0. So this is a number. I'm not taking the product, mind you. These are just the digits. So if I have a 3-degree polynomial, say 4, 2, 3, 1, then what I mean by it, this notation is just 4, 2, 3, 1, not the product. Okay. What is this called? Does anyone know the formal name? This is called the base 10. Now I tell you that call this A.
Isn't A just P of 10? Like,
Yeah.
The thing that we have written as A, isn't it just P of 10? Like, we can just put in, that would just
Yeah,
be the
that's P of
base 10
10.
representation.
Sorry. Can you repeat that? My connection just fluctuated for a second.
Oh, so I was saying that the number that you have written as A with that overline, that isn't that just P of 10? You can replace X by 10 and get that.
I'm not sure what you want to say.
So he's saying that if we write that number down, then we can write as a n into 10 to the power n minus 1.
Yeah, definitely.
So P of 10
is just P of 10. Absolutely right. I heard something else. Sorry. Yeah, so this is P of 10. Okay. So in fact, for any base k, this is just P of k, right? So if this is a base k representation, then this is just P of k. Right, nice observation. Okay. Now I tell you that this A is a prime number. Okay. So can you show that Px is irreducible? This has very far-reaching consequences in abstract algebra again. In the study of something called ring theory. And leads to something called Galois theory. But it's a very interesting Olympiad problem to look at as well. So let me write down that suppose he's a prime. Show that Px is irreducible.
Can we go by contradiction?
Yeah, sure, why not?
Like if we take Px equals to some Gx into Hx, then we put 10.
Go ahead. I just want to see, develop an argument.
Will we need to use that divisibility by integers criterion in this somehow?
Divisibility by
Integers, that a minus b will divide
no,
p
no,
of
no.
a.
This is not that sort of a problem. This is you can try the problem in several ways, but I would suggest try it out by complex numbers and bounds on modulus and such things.
I was thinking of something, maybe I'm wrong, but
Yeah, go ahead.
if
If you have an
if
argument,
p of x was if p of x was reducible, then p of x would have a root, like say alpha.
okay. I mean,
Oh
no.
no,
No?
no,
Wrong
it might
assumption.
not. Right. Okay.
Wrong assumption. I mean,
Yeah,
P
it
of
might
X
not
has
be
a
linear. I understand.
What you want to say that P of X has a real root?
Yeah.
No, that might not be true. There exists several proof of this criterion and several very brilliant proofs, but I'll give you a proof that will help you to essentially solve other types of irreducibility problems. Okay, it's a very general. Let me write down the result for you. A result. Okay. Okay. So let Ex equal to n x power n plus n minus 1 x power n minus 1. I'll give you hints to solve this result, but the proof of the result you have to do it on your own. Since I'm running out of time. If you cannot, you definitely should contact me. Okay. And okay. This is a polynomial with the leading term coefficient not equal to 0. Okay. So it has degree n. Okay. I define something like let m equal to maximum of say 0 less than equal to k less than n mod of ak by n. So I'm looking at the maximum of this kind of quantities, a0 by n, a1 by n, all the way up to n minus 1 by n. Fine. Then all roots of px are less than n plus 1 in modulus. This is a very insightful result. It gives you an upper bound on the magnitude or the modulus of the roots of a polynomial.
Was there a similar question like this in a past ISI entrance exam? I mean,
Perhaps,
it
but
was very
that
similar.
was a little bit different. As far as I remember, that was a little bit different bound. It was probably asked to prove that the roots, I mean the modulus of the roots, lie between something like this quantity, 1 less than equal to k less than equal to n. Sorry, this is also a good bound, and it would be very instructive to try and prove this. Okay, another bound I should write. Possibly ISI asked something on the lines of this. And I'll tell you a very interesting thing here, that this can be proven easily by whatever we have done, we have learned today. And I'll not be so much vague. Use this. I'll put a star mark. Okay. So it will be an interesting exercise if you go ahead and try this. Okay. What is this region called? What should we call this region? I mean, a little bit of coordinate geometry, perhaps. What is this called? Yeah. Yes.
A few minutes. I got disconnected for a few minutes.
Okay, so till when did you follow?
Yeah, till that it was P of 10 till that point.
Sorry.
Like till that point where we were discussing that P of that up to a naught is P of 10.
P of n. P of 10. Okay, P of 10. All right. So I didn't say much after that. I completed this problem by saying that suppose A is a prime, then show that this polynomial Px is irreducible. Yes. Okay, that's all I said. And here I stated the result, and it's very, I mean, self-explaining what I've written down. So, can anyone tell me what this region is called? I mean, you should definitely know what this region is called. If suppose I was a JEE instructor and I told you that what is this shape, I mean, I don't even want to give options on this, then that will make it very obvious. It gives this gives a region, right, in the complex plane. And it's a region between two circles, isn't it?
Sir, beyond this region, the
Donut.
polynomial will go to plus or minus infinity, or minus infinity, or plus infinity, or something like that.
Yeah, but what I'm saying is the roots of this polynomials. These are the roots. All the roots of this polynomial lie inside this annulus. This is called an annulus, shaped like a donut. Okay. So this can be proved, but now so this is a very similar looking bound actually. Okay, pretty similar looking bound, and I will tell you how to prove this result. I mean, I'll give you a brief idea. Proof. All right. So again, triangle inequality is what comes to our rescue. So suppose alpha is a root of 2x. Proof of what? Proof of result. The result that was stated in the previous page. All right. Now, so P alpha, or to be more precise, mod P alpha is equal to 0. And again, by using triangle inequality, this is what I mean we have used throughout today. This argument. And see, it is a wide bunch of applications. Okay. This was what we had. And I'm sorry, this will be A0, right? Okay. So now I can use triangle inequality and I can write this as n alpha power n minus m alpha n. Anyone objects why I'm doing this? Why I can write this?
We're basically
M?
just multiplying and dividing by mod an.
Right. So this step is clear to everyone, right? Well, let me write down n. What was n? It was.
Sir?
Yeah.
Can you just stay here for like 15-20 seconds?
In this page. Oh, all right, sure. Meanwhile, keep on thinking that why I can provide such a bound. If you have not already thought.
Oh, yeah. I mean, I just like I was disconnected, so I not.
Yeah, sure. I was telling to the rest of the people. You keep on writing.
Yeah, because since m is maximum, we are taking something bigger than subtracting something bigger than.
Right. So we can write that inequality. Okay. Tell me when you're done. Okay.
Yeah.
You're done, right? Okay. So I'm writing this. And now can you finish the proof? What I want to show is that mod of P alpha. Sorry. I want to show mod of alpha is less than
m plus 1. So if we take alpha, if we take that negative term to the other side.
That negative term to the other side. Okay, take it.
And then we divide by.
Or maybe you can just perform the sum of the geometric series in question.
Oh, yeah.
still, I mean, I don't want to finish this proof from here. You should be able to do it. So try and finish the proof. This kind of argument we have been using all day. Okay. Now the interesting part is that how do you use this result to solve this problem? So it was a very nice observation, and Shevonti possibly said that we should proceed by contradiction, right?
Yes, Dada.
Yeah, so combine your ideas. One of you said that P10 is essentially the prime number we are looking at, and one of you said that we should proceed by contradiction. Now proceed. I mean, combine.
There I got that G10 should be 1 or H10 should be 1.
Okay, so what you are writing Gx as
Gx into Hx.
just a second, let me write down proof of Ohm's criterion. Gx is equal to Gx into Hx. So P10 is equal to G10 into H10. Now
One of them must be 1.
one of them must be 1. Without loss of generality, assume that G10 is 1. So what is mod of G10? Assume that its roots are, say, let's say alpha 1. I'll write down directly. I mean, okay. Alpha 1 all the way up to alpha k are roots. Huh? Now use the lemma. So every root has modulus less than 1 plus m. So what is m in this case? Yes. What can I say about mod of alpha I? See, these are essentially decimal representations, aren't they? So all the coefficients are between
0 to 9.
0 and 9.
So all must be 9. I mean,
9, I can do better. Trust me, I can do better. Can't I do better?
so since alpha is and mod of g of 10 is mod of g of 10 is 1, then we must have
So what is m again? Maximum of 0 less than equal to k less than equal to n mod of ak by n. And here we will not look at ak. We will look at the coefficients of this polynomial, G polynomial. So let the G polynomial be something like, let G10 be x power sorry, bk x power k plus bk minus 1, sorry, gx k minus 1 all the way up to b1x plus bc. This is nothing but bk by bn. See, I mean, you are getting px by taking the product of these two polynomials, right? So the coefficients of px are essentially product and sums of the coefficients of gx and hx, isn't it?
Yes.
So yeah, so what can we say about the maximum of this? So we must look at the case where bn equal to 1. Can bn be 1?
What is Bn?
Sorry, I'm not talking about, I should have written used a different variable, isn't it? 0 less than I less than k. And I should write bi by bk. So can bk be 1? So think about this. I mean, I'll tell you something else, that suppose bk equals to 2, then are we done? Then this maximum should definitely be less than what? 9 by 2, isn't it?
Yes, then we are done.
Then we are done. Why? Because then this is less than 9,
Yeah.
and
So
that's all we
it
need, because
will not
then
be 1.
10 minus alpha I, that will be greater than 1.
1.
So G10
Yes.
will be greater than 1, which is a contradiction, because my assumption was G10 was equal to 1. So the only thing that I need to show here is possibly why.
Dada, I have a doubt. I missed something in the proof, in the beginning of the proof. So
Yeah.
why is that mod of g of 10 equals 10 mod of 10 minus alpha 1, 10 minus alpha 2 all the way till 10 minus
Because
alpha
I have
k
assumed that alpha
greater
1
than
to
1?
alpha k.
No, yeah, why is that greater
No.
than 1?
I wrote that just now. I mean, after this step. After
Okay.
this step. Okay.
Okay. Oh, then why is 10 minus alpha I greater than 0?
See, if bk is 2 or more, then definitely m will be less than equal to 9 by 2. Isn't it? In that case, mod of alpha I, so I should write this step after this step, right? This comes after this. So mod of alpha I will be less than equal to 1 plus 9 by 2, which is trivially less than 9. That implies, so this would imply mod of 10 minus alpha I is greater than 1. Right? And so my choice of alpha I was arbitrary. So all of these are greater than 1, which implies that this should also be greater than 1. Right?
Yeah. Okay.
Okay, so can I leave this as a small exercise here? Because it should be visible by now, isn't it? Okay. So try and tell me whether mod of alpha I less than 9 always holds. That is all the roots, whether they are less than 9 or not. That will complete the proof. Because by assumption, my G10 was equal to 1. And now I've got something like mod of G10 is greater than 1. So let me write down that using the bound alpha I greater than, less than equal to 1 plus 9 by 2, which is essentially less than 9, gives me 10 minus alpha I is greater than 1, which in turn implies that G10 is greater than 1. Contradiction. Okay. Fine. So, all right. So I had left.
Sir?
Yeah.
Sir, alpha I cannot be negative, right? Alpha I?
Alpha I are the roots of this equation. They have, I mean, if why can't they be negative?
Then
I mean, no, they cannot be negative. Yeah.
Yeah, so if they cannot be negative, then if we take the coefficients,
Right. So
bn minus 1 is the sum of all the alphas, and then we take the average.
Right. Okay. Then
we have then yeah, so pk minus 1 will be the sum of alpha i's, negative of the sum of alpha i's. So
anyway, I mean, does it matter whether alpha is a why I would like to listen to your argument again. Why alpha is cannot be negative? They can be negative, right?
I'm a little confused, I think.
If they're negative, then this inequality will still hold. Think about it. Okay. So that's all I more or less what I wanted to cover. So if you have any kind of doubts or you need any sort of clarification, try out the things that I left as exercises in between. And all right. So I left you a problem at the end of last class. I mean, that is very unrelated to what you are studying at the time being. So could anyone come up with a motivation of a proof why all polynomials in Rx of degree greater than 3 are reducible for the even case? I mean, this is unrelated to what we are studying. Okay, so this is just a discussion. What is the result that you think that will come into crucial use here?
If the degree is odd,
then we are done. Then
we are done by
owner
we'll get something.
Yeah. Or even degree.
For even degree, we know that the I mean, if there are roots, then we are done. Suppose there are no roots, then we will have roots in complex conjugate pairs.
In complex conjugate pairs, fine. Then
So suppose the roots are Z1, Z1 bar, Z2, Z2 bar. We can just pair and multiply the X minus Z1 and X minus Z1 bars. We will get something in reals.
ZK bar, right?
Oh yeah. Sir,
We
since
can just multiply. So if Z1 is X plus IY, then Z1 bar will be X minus IY.
X minus IY. So if we pair them,
we can pair them and multiply.
All right. So this is a very easy fact, but I just wanted to point out that our study of irreducibility is complete in some sense, because yet your study and X we have no irreducibility for T. So whatever we are doing, we must restrict it to ZX, CX, QX, and modular P's. I mean Z mod P, ZX. Okay. So the answer to this will be yes. And someone was saying something else?
no, sir. The same.
Okay. Fine. So that more or less completes our study on irreducibility and some related polynomial topics. Okay. So any questions? Try this out. Okay.
Will we have only 2 algebra lectures for this workshop, or will there be more?
I mean, what is your verdict? Should there be more? I mean, I will not be there. This is probably my last.
Oh.
If you want more, I can convey at least to the other people who are teaching.
I mean, yeah, more is always better, I guess.
Okay, so yeah, I'll definitely forward your request to the others. Okay, so whatever I taught, I mean, not just whatever I taught, but any problems you have regarding algebra, not even outside the domain of polynomials, you can send those problems to me. I'll look into that. Okay.
And Nada, can we please get this PDF?
This PDF. Sure,
Yes.
sure. I'll just export it after this. Okay, and the PDF of the previous class as well. Okay.
Thank you very much.
Okay. So, any other questions? How are your mock tests going?
I think the first mock test was the toughest till now. The second mock test was a little bit easier, but still okay. I was really confused during today's mock test. I don't know. I mean, some questions were nice, like the 7th and 8th questions were ISI appropriate questions, but I was really confused with question number 1.
For question number 1 of the subjective, I have no clue about the subjective, but there were a few questions in objective which at least the combinatorics ones were given by me, I guess. So could everyone solve problem 1 of objective?
Yeah.
How did you do?
I did it in that way that suppose there are 10 dices. So first I throw all the dices, except the last one. Right. So that can be done 9 ways. Now the last dice only has one chance. That is, if it's 6k plus 1, then it will have to be 5 and so on.
Perfect. But do you see an interesting probabilistic fact here that any divisibility by any modulus, any remainder with respect to 6 will have the same number of cases, will have the same number of occurrences? Do you see that? I mean, not just number of cases which are divisible by 6, number of cases which have remainder 1 when divided by 6, which have remainder 2 all will have same number of cases.
All will have, yeah.
Okay. And could you solve the binary strings one?
Didn't do that. That was the only one I didn't attempt.
Anyone tried that?
I tried it during the test, but couldn't due to the time limit. I just thought of an approach like
recursion.
Yeah, probably recursion. I thought of it like representing it in the integer lattice So if you the question was equivalent to finding a path under the diagonal from 0, 0 to
Good
n,
idea, good idea. But could you implement it?
No.
Yeah. So you should look into something called very interesting. You might even ask your combinatorics teacher, whosoever will be teaching you, to bring it up in the class. Just a second. Bit of charge. So you need to look into something called Catalan numbers. Okay. So read up the material in Catalan numbers. It's very, very useful and has a wide variety of applications in maths, not just maths, but
it was similar to the question that with opening brackets and closing brackets.
Opening brackets, number of well bracketed expressions. Exactly.
Yes.
Exactly. Nicely spotted.
Yeah, I was kind of remembering it during the test, but couldn't use it without the proof. So.
Yeah. So, okay. So that's more or less it. So thank you for attending my class, and all the best for your upcoming. So how many of you are taking the ISI entrance this year?
I am.
I am too.
Okay, so it's 2 people. So okay, best of luck. Thank you. Bye.